So our next speaker is Dr. Armin Iraji, who's an assistant professor in the Department of Computer Science at Georgia State University. He's also a member of the Imaging Hub at Georgia State, and he's a core faculty member at the Trend Center. Dr. Iraji has been doing some pioneering work in estimating spatial dynamic networks from fMRI data. So it's a nice complement to MEG, where you have a lot of temporal resolution in fMRI. We're leveraging the spatial resolution in this work, as you'll see. So I'll let you take it away. For your slides? Okay, good.
Hello, everyone. Today I'm going to talk about spatial dynamic and some of its application. And I will start by reviewing some of the basic concepts that I believe it allows us to better understand and appreciate spatial dynamic. I have nothing to disclose. Okay, so in general, the goal of functional connectivity study is to understand and evaluate the interaction across the brain. Essentially, the idea is the brain consists of a set of functional units or functional sources, and we want to estimate the interaction among them. Each functional source can be defined in a lay term as a region with similar functionality and can be characterized by two elements. It's a spatial pattern that describes its distribution across the space, and temporal pattern that describes its activity over time. So our ability to estimate the functional connectivity depends on how well we estimate these functional sources and interaction between them. The most straightforward way is to use an atlas and approximate each functional source using a spatially fixed parcel. And then we calculate the average time series within each voxel as a representative of the time course of that functional source, and simply calculate the temporal similarity between these time courses to get what we call functional connectivity matrix. So we get one functional connectivity matrix for each subject, and then we use them to study brain. While this approach has been pretty helpful, and they consider variation in connectivity pattern, they do not consider variation in the spatial pattern of functional sources. So given the fact that the estimation of these functional source, these time courses and their functional connectivity depend on the estimation of these functional sources, accurate estimation of these functional sources are necessary. And if we have inaccurate estimation of these spatial pattern, it may lead to suboptimal estimation of these time course and therefore their functional connectivity. To overcome that, we can use a data-driven approach and estimate these functional sources or functional unit directly from data itself. One way to do it, different way to do it, one way is to use ICA, decompose the brain to a set of intrinsic connectivity network, and then calculate the temporal similarity between these time course, and what we call them is functional network connectivity, just to make a distinction from the classic one as we are optimizing for identifying subject-specific functional sources. So this method is good, it's helpful, it allows us to capture variation, account for variation in both a spatial pattern and connectivity pattern, but still it does not account for within subject variability. Given the brain is dynamic, there is no reason to assume these connectivity matrices stay the same over the course of the scan over time. So over the last decade or so, there has been growing interest and effort to quantify these time-varying functional connectivity. As a side note, I just want to point out here when I'm talking about within subject variability, I'm talking about over the course of a scan, over the time, not between like two sessions or between task and rest data, which these data-driven approach perfectly do fine. Okay, so figure on the left show an example of classic time-varying functional connectivity analysis. First, we run an ICA to get the intrinsic connectivity network and their time courses. And then instead of calculating one functional connectivity using full time series, like what I did on the left, what we are going to do is we are going to apply a sliding window We estimate the functional connectivity for the first window, then we shift it, we estimate it again, then we have a functional connectivity as a function of time-varying functional connectivity. And we call these time-varying feature that we extract from the temporal pattern of functional sources, temporal dynamics. Figure on the right, I'm showing an actual example of one subject that we try to estimate these time-varying patterns using a more recent approach that leverages time-frequency connectivity analysis. Okay, so these approaches push the field forward. It allows us to capture within subject variability, temporal dynamic, but they do not account for variation in the spatial pattern. The same way that the connectivity interaction between these networks can vary over the time, the spatial pattern can also evolve over the time and go under changes. After all, brain is dynamic, and we can have a variation in the regional contribution. And that is the focus of spatial dynamic analysis, to identify and capture these spatial variation of functional sources. And keep in mind, as I mentioned earlier, accurate estimation of these functional sources are essential to have a good and optimal estimation of functional connectivity as well. So there are different ways to capture the spatial dynamic. This is one of our earlier work, where we try to estimate the spatial dynamic of a large-scale network using their spatial basis. Basically, it's a two-level analysis. We first run a very high model order ICA to get the subcomponent or basis of functions, these large-scale network, and then we use those to reconstruct these spatial dynamic. Here, in fact, we are pushing the problem a little back because we are assuming those bases are spatially fixed, while we ideally want to allow a spatial variation at a different level of function hierarchy. But still, we can get some spatial dynamic. On the positive side, by imposing this constraint on the extent of spatial variation, we can capture the spatial dynamic even when the temporal segment does not have sufficient information to fully quantify spatial variation. And after getting this spatial variation, we can, for example, do a clustering and find the most recurring state. On the right side, I'm showing you two examples of variation in regional contribution across different states for the frontal parietal and subcortical network. The variability index, which quantify overall spatial variability, suggests that frontal parietal network and other networks that are involved in higher level tasks have a higher spatial variation compared, for example, subcortical, which in this study show least spatial variation. And we can use these to study, for example, schizophrenia. So we saw across different measurements, for example, the number of the transition between different states, in the fraction rate, in mean dwell time, we see a significant difference between two groups. For instance, we see individual with schizophrenia spend less time in the coherent state 2 and 4, which is also consistent with the concept of disconnectivity hypothesis. We can also look at the spatial variation, and we see significant differences in the region that show a group difference across different states. Here I'm zooming in for the attention. You can see in state 1, S1, and state 2 and 4, different regions show group differences. We can even go further and try to find which dynamic state of this network co-accord together to get like a global pattern and use those to study the brain. We can also quantify a spatial dynamic at voxel level resolution, for example, using a sliding window, ICA or IVA, or here correlation. The two figures on the top left show two examples of spatial variability. Green show the level of the coupling variability over time. And if we do a voxel-wise comparison, you can see the region that show group differences are quite different than regions that show group differences in the static analysis. So if we limit ourselves to spatially static analysis, we are going to miss these differences. I will provide more examples as we move on. And considering that we are working in space, we may want to summarize these spatial variation, these high dimensional data. One way is what we did here is kind of transition matrix. We count how many times we move from one intensity beam to another. and then we can use these summary measures to study brain. For example, here we can see individual with schizophrenia have a higher rate of fluctuation in low amplitude compared to control. We can even move further and extract a global index, like spatial uniformity, spatial temporal uniformity, or energy index and contrast, and use those to study brain. We can also look at the dynamic state. Here I'm showing the three state of default mode network in RGB additive color. So white area is the area that contributes to default mode in all three states, precuneus and posterior cingulate cortex, which is not surprising, as they are the part of the core part of default mode. But you can see the thalamus is contributing to default mode only in state 1, not the other two states. And this can potentially explain the inconsistency we see in the spatial static analysis. Some study reported that the thalamus is a part of default mode, some report is not. What we see here is part of default mode, but only in a specific moment of time. And depending on what segment of the data you are analyzing, you either see it or not. You can see the similar pattern in the frontal region. Different areas show a contribution to the default mode at different states. And if we look at the voxel-wise comparison, we do a statistical analysis. For example, in subcortical, in the static analysis, you see some areas show group differences. I don't know if you can see, yeah, some group differences. But when we move to the dynamic analysis, we can see huge part of the subcortical show group difference. So what is happening here is, when we do a static analysis, we kind of average out these differences that exist. Here we are lucky, we still see some differences in the static analysis. But if we look at the somatometer, static analysis didn't show any group differences, while we are seeing huge differences in the dynamic state 1 and 4. One interesting observation I want to point out is the importance of the cerebellum and its transient contribution to different large-scale networks. The contribution of the role of cerebellum was underappreciated for many years. Although recently we are seeing a study more in the role of cerebellum in this large-scale network. Here I'm trying to point out that you want to study the role of cerebellar region from a dynamic point of view to understand how these transient contributions play a role in those networks. The other interesting observation is the level of spatial integration and segregation between these networks, which suggests maybe these networks are not as isolated and especially non-overlapping as we thought they are. One way to quantify that is to calculate the time-resolved spatial coupling by measuring the spatial correlation, and do the same analysis that we do in the dynamic functional connectivity analysis here on these spatial coupling network matrices. And as an example, we see here that in the dynamic state 1, we see 6 specific differences in the schizophrenia, including spatial coupling between the default mode and salience, which also shows significant association with the polygenic risk score for schizophrenia. One thing I want to point out here is that the analysis we did in the voxel level analysis for the salience network state 1. The region that show group difference are the region that we commonly associate them with the default mode, and we mask them out when we do a static analysis in salience. So these low contribution, this region with low contribution play an important role for these 6 specific differences that we will miss them if we were just using a static analysis. This is also related to another work of us where we show in the last paper, we show the time point with low contribution plays significant role and have unique information. So in both time and space, these low amplitude, low contribution, this data point with low contribution carry unique information, and we should not just discard them. That work was about event-based approach and CAP. I don't have a time to go over them today, but I'm happy to chat with you about those as well. And finally, we were interested to also look at the spatial dynamic from nonlinear perspective. So most studies that quantify and capture the functional sources or brain network leverage linear interaction, despite nonlinearity across a different level of neural computation. So here in these last 2 work, we use the concept of connectivity domain analysis to quantify these functional sources and brain network by leveraging nonlinear interaction. And we have a very interesting result. You can refer to these 2 papers or talk with Spencer tomorrow and Thursday. He's happy to share with you very interesting finding he had. But what I want to point out here is I want to compare the spatial dynamic of linear and nonlinear aspect of these networks. So we can see on the left an example of one actual subject, linear and nonlinear. You can see the level of spatial variability in nonlinear interaction, nonlinear network versus linear, including spatial integration and segregation with the left frontal parietal network. So here we try to quantify them by applying clustering and matching the state between these two. You can see in the nonlinear, we have a higher rate of variation across different states. We also see a higher rate of, we can call it faster speed these spatial variation in nonlinear, which we try to quantify using L2 norm distance. Interestingly, this also shows significant group differences, which kind of related to other observation about the fact that schizophrenia working more in high frequency fluctuation. Happy again to talk about them later, but since I don't have more time, I'm going to point out many of these tools and many more that are focused on temporal dynamic have been implemented in the GIF toolbox. This paper provides a gentle introduction in the dynamic in general, including spatial dynamic. It has a walkthrough and tutorial about how to use these toolbox. We have even a tutorial video. And if you have any question, I will be happy to answer and help you out. And I want to thank you all for listening to my talk. And also, if you are interested for what we are doing, we have an open position. Please reach out to me. Happy to chat with you. Thank you. Mm-hmm.
Thanks, Armin. One question from the app is, how do you select the window size, and how robust are these patterns to the selection of that window?
Okay, so window size, in fact, in the last paper I show you, we are suggesting some specific window size that you can look into, but also in the work that I showed earlier about time frequency analysis, if you recall, we are kind of trying to overcome the need of using the specific window. But if I want to give you a rule of thumb, I would say like go with the 60 to 30 window, 30 seconds if you are interested on this. Mm-hmm. What was the other question?
Just how robust the results were.
Across a different data set and also across different clustering number, we see a similar pattern, basically.
Mm-hmm. Oh, wait, did we? Oh, yeah, so here's one. I'll just read the whole thing. Hiya, Armin. Lovely work.
Thank you.
How did you compute networks using the nonlinear method?
Okay, so you can feel free to talk with Spencer in tomorrow's, he has a poster on that. But basically, there's a concept of connectivity domain. What we do is we calculate the nonlinear interaction for whole brain, voxel by voxel, and then we remove the linear part to get some sort of explicit nonlinear, and then we apply ICA, as always. I'm a fan of ICA, of course, no need to say, to get these networks.
Great. Okay, thank you very much.
Thank you.